I just want to go back and watch that Hot Wheel jump thing like 100 times. That was like the coolest thing ever. So thank you very much, Mouse. Now I would like to turn it over to Jim Rusk, the Chief Technology Officer for Siemens, and his group, who are going to come up and talk about breaking down the barriers to innovation. Jim?
Okay. Thank you, Tom.
Thank you.
Well, good morning. And we're really excited to highlight some of the core capabilities and features of our digital innovation platform. And we're going to be talking about that through the lens of peeling back the onion of the technologies that we're delivering. Now, we heard Tony mention yesterday Thomas Edison and the invention of the light bulb and what the impact on society as a result of that happened. But he also mentioned the electricity grid, and that was introduced by a gentleman named Samuel Insull here in the US. And really what he was able to do at the time, the different power companies were delivering power to people's houses and businesses in a very inconsistent and sort of unreliable way. And what he was able to do was link those together into a common grid and be able to bring together these disparate systems, open it up for millions and millions of people to take advantage of this great technology, in this case, the light bulb and electricity, and then ultimately help the companies that are delivering this power reduce their operating costs and benefit society by making it just a part of everyday life. Now, for us in the Digital Innovation Platform, and we saw a glimpse of this yesterday, and probably during the conference you've seen pieces of this. We're going to bring this together today in a series of examples. But what we're really talking about are our domains and the areas that we deliver applications that you all are very familiar with. We can see some of them highlighted here, but principally, you think of us as delivering these excellent applications that build geometry, that build electronics, that simulate that manufacture that gather data and perform analytics against those in-service products. But that is also linked together to enable collaboration and connectivity through core services that we bring to bear with our products. And you would think about this typically as something like Teamcenter and something like MindSphere for cloud-based IoT. So we break this out, and we want to highlight a few of the products, and we're going to actually be walking through a series of these products during our discussion. But the important element here is excellent applications with the heavy lifting of integration of these applications across the innovation platform. So, we really try to, with our platform, our applications, and our integration, get everybody plugged in to the life cycle, into the process of innovation. And this helps for flowing of information, for clarity of the information and the process, and how teams are able to collaborate together. Now, you might be thinking, well, geez, that's really nice for big enterprises and how they collaborate across the enterprise. But in fact, this really is addressing the whole gamut of applications. And whether you're a large enterprise or small business, you saw on the previous two slides that we have a series of applications. And of course, one of those great applications for individual productivity is our Solid Edge product and the whole suite of applications that come around that product stack. So providing really beautiful productivity tools that allow you to design any number of kinds of products in a form that best suits your needs and your company's needs. Furthermore, these applications all do connect to this digital thread to enable information to flow both within your enterprise, but also with your supply base and other partner companies that you might be operating with. And one example of this that I want to highlight is a company in the Netherlands. It's called IHC. They're a shipbuilder. And this company uses Teamcenter as its digital backbone, providing information collaboration services, handing information across different applications. But it also provides the opportunity for us to deliver our NX products as an example for the overall ship design, but also they have been long-term users of our solid edge products for the equipment. These are, let's say oil kinds of service ships that deliver equipment and do other kinds of things in the oil rigging process. And they also are dredging equipment. So the equipment on the ship is actually developed in solid edge. And in that way, we're integrating these applications and the data and allowing it to flow through the common backbone. Now, collaboration, I think, for all of us, and we're a software company, but we also have to collaborate across our organizations, can be a challenge for us. We have different domains, people with their heads down, doing their work each day, trying to drive to the best decision, the most optimized decisions that they can for their organizations. And so we see mechanical departments, electronics, software, and those organizations oftentimes are self-optimized, but not cross-organization optimized. And what we're driving with this digital innovation platform is better connectivity, more effective and easy ways to share information and keep the process flowing together across these different domains. One of the most striking examples of where this really has to work is in the area and the linkage of the virtual world, which we all collectively as organizations have experienced with our products for many years, and then delivering that to the physical world and then back to the virtual world. And so this closed loop feedback, the completion of the digital thread, all the way from virtual down to gathering in service information, whether it's from your shop floor or from the in-service product, and feeding that back into the virtual world where you can make adjustments, make changes, make fixes as appropriate based on the real-time production data or the real-time in-service data is enabled through our digital innovation platform. So more and more we're linking these together. MindSphere is the way that we're linking the information from the in-service and shop floor data through the cloud back into the virtual world to be able to make decisions real-time with how the product is performing. Of course, one of the key areas for us is how do we deliver this information? How do we help people understand it? And of course, a central tenet to this is a picture tells 1,000 words. And so visualization is a part of everything that we do. And we see a few of the graphics of different applications highlighted here, but we're no longer satisfied with just sort of basic visualization. We're now driving into virtual reality, augmented reality. We'll see some examples of both of these in the presentation, but helping to enhance your experience with our products through things like virtual reality. And by this, we don't mean pumping out files to some other system and being able to then call up some virtual reality tool and then do your work. We want to drive, we have driven this directly into our applications. So if you want to run in virtual reality mode with NX, you say virtual reality mode, and there it is. So this whole idea of using virtual reality for design process, reviews, simulation is critical. And the Digital Innovation Platform is how we're integrating this information, both the excellent applications that we deliver along with the digital backbone to be able to allow collaboration and connectivity. Now, through our discussion today, we're going to be highlighting several areas. The first is going to be with e-aircraft and some examples there. And then we're going to walk through some other companies and examples of how our products are delivering innovation and application excellence for the digital lifecycle. So let's begin first with e-aircraft. And I'd like to introduce Ganesh Sethuraman to the stage here to begin our first segment of the presentation.
Thank you, Jim. Thank you. So the first customer I'd like to talk to you about today is e-aircraft. And I'd like to talk to you about how they use the Digital Innovation Platform at their location. Now, if I go, I think the one thing that's really cool about the story is that you might have heard Tony Himmelgarn often talk about how not only do we give you the ingredients to make your lunch, but we actually also eat our own lunch. And what we mean by that is, at Siemens, we actually use our own software. And this is a case where we have one of our sister organizations within the SimCenter family, the Siemens e-aircraft company, that basically have a mission. And their mission is to disrupt the propulsion in the aviation industry and develop electric propulsion. Now, one thing that's interesting is what Dr. Frank Anton, who is the CEO of the e-aircraft team, has said, is that he believes that there have been three pivotal moments in the history of aviation. The first one was in 1903 when the Wright brothers had the first engine-powered aircraft that flew for a total of 12 seconds. The second one was in the middle of the 20th century when we had the introduction of the turbofan engine and ushered in the jet age. But they believe that they're on the cusp of the third generation, and this revolution is electric. And the question is, why is this happening, and why is this happening now? So what you see here is the first driver that we kind of see, in that if you look at commercial aviation, they're always trying to maximize their revenue. And it makes sense when you look at their cost structure. If you can kind of see in the bottom there, you can see the total cost of ownership for most airlines. And more than half of it is driven by fuel costs. And while the fuel prices may change, it's always going to be a large factor in it. And so one of the things that they want to do, anything that they can do to reduce that and makes it highly desirable. A second driver is regulation, environmental regulation. There is a regulation on the books that by 2050, there has to be a 75% reduction in CO2 emissions. Now, part of that might be available, might be possible with existing technologies, for example, the use of composites for lightweighting. But the only way we're going to achieve this kind of radical reduction in CO2 emissions is through the use of disruptive technologies such as e-propulsion. Now, a third and not insignificant perspective and a positive byproduct of e-propulsion is the fact that normally these are fairly, the noise levels of these is significantly less than traditional engines. And this isn't just a nice to have, but this can have a significant impact for the companies, as there's often legislation in many countries to stop or not have night flights.
So in other words, Ganesh, so for people like myself and Tony and Bob and many others in the audience that arrive in Europe, we might be able to avoid to arrive there at 6 a.m. in the future. Is that what you're saying?
Exactly. That's exactly what it is.
Okay.
Yep.
So as a result of quieting down the aircraft and...
Right, because what happens is with the noise pollution, basically, that's happening, is that, you know, all the local populations, you know, there's legislation against that.
Yep.
And so this also helps for the airline's bottom line because they can extend the operating hours and, of course, again, the convenience to the customers. So that's all fine and good, but how do we get there? Well, there are some big engineering challenges to get to that. And the key first is to get the right power density. Now, what you see here on this graph is a graph of, over the last few years, of different manufacturers who have been developing different e-propulsion systems. And you can see on the one side, the power output that's being generated. Now, currently, the conventional EPUs, or electrical propulsion units, the power density is about 1 kilowatt per kilogram. And what you can see highlighted in orange are the projects in which Siemens has been involved in. And in the first generation EPU, they were able to get, and this is in 2016, a record 5.2 kilowatts per kilogram. But then you can also see that to achieve full EPU, full electrical propulsion, you need to get to about 15 kilowatts per kilogram. So that's still quite a ways away. Now, how were they able to do that? Well, one of the main ways that they were able to do this is by reducing the weight and reducing the size of this. But as you'll see, the only way they were able to do that is by using the tools from Siemens PLM software to analyze all this together. And so, like I said, for them, what they did and what they started to do was reduce the weight and reduce the size. And they started that by, for example, optimizing the structure of the EPU. But by optimizing the structure and reducing the size, that also creates a second problem because there's a lot of heat generated. And we need to be able to reject the heat and remove the heat. But if you don't, because if you don't remove the heat, that could lead to demagnetization of an electromagnet, which would basically cause a catastrophic failure because it would stop rotating. So even if you could then address all of these problems, we still have to make sure that this specific EPU matches and is tuned for the aircraft in which it's going to be used, the mission profile, and its operating environment. So let's jump now to what they've been working on, the most current generation, the SP200D. And what you can see here on the right is an image of the motor in question, where you have this outer stator that's static and an inner ring that rotates. And in this case, they were trying to focus on trying to reduce the, increase the torque density, not so much the power density. And the main reason was that they want to have it optimized for high torque and low speed, and using it in applications, in this case tuned to a specific application that you can see on the top left, which is a prototype that's being developed by Airbus helicopters called the City Airbus. And it's being developed conjointly with the Siemens e-aircraft team. And what it is it's basically a flying taxi. It'll take 4 passengers across an urban environment, and it has 4 sets of these dual rotors, and they're propelled by the Siemens EPU. So let's take a look at how the Siemens e-aircraft team was able to take advantage of the Digital Innovation Platform. Now, of course, you'll see that they use a lot of our solutions on the mechanical side, electronics, analytics, and software, and of course, all of this managed inside the Team Center. But one of the areas I want to focus on today is on the simulation side. Now, I don't have the time today to talk about all the different simulations, but I do want to give you some highlights of the types of challenges that they had, where really what you see here was that the only way they were able to achieve this was that they had to look at this from a multidisciplinary, multi-physics approach, and they had to do a lot of co-simulation across the different products. So what you're seeing here first is that they were able to use Magnet, which is from Infolitica, which is a company we acquired via the Mentor acquisition, to do the electromagnetic analysis. And what you're seeing here in the animation is basically a cross-section of that motor, the outer ring and the inner ring, the outer ring being the stator. In this case, is moving, but in reality would be static. And you can see the electromagnetic field that's repulsing this inner ring. There's a gap of about 1 millimeter of air, and that's allowing it to move. Now, of course, the thing is, this is also oil-cooled to reduce all the extreme heat that's being generated, but that's not enough. There's also additional heat that happens, and therefore, you need to do further analysis. In this case, then they started going to SimCenter Star CCM Plus to look at how to have it air-cooled and reduce some of that heat as well. So in this case, you can see how it is actually being used inside the City Airbus, where you have the dual EPU, and you can see both EPUs rolling in different directions. And you can look at the airflow first, and you can also look at the heat dissipation, because the key here is that you want to have convective heat dissipation and convect away all that heat that's being generated there. So the thing is, to be able to do this, they had to combine both these simulations together, do the co-simulation, and it's the combination of the CFD, the thermal, and the structural analysis that allowed them to deliver this type of well-balanced motor. But as I said before, that's not enough, because they also need to look at it from the perspective of the operating environment. And what you're seeing here is by using SimCenter AimSim and connecting it to a flight simulator, they're able to simulate and effectively virtually fly before they build it. So they can look at the flight profile that it wishes to take, and that's what you can see in the corner there with the little dots. It's saying, okay, I want to go from point A to point B and so forth. But then they can also do what-if scenarios. So what if, for example, one of these dual EPUs breaks down? Can we then survive, and can the other motors still hold on to it? So basically, I think I hope what you saw was that with our tools is the only way they're able to innovate and generate such an EPU. And the interesting thing is that within my lifetime, the history of aviation will change. And the Siemens aircraft team believes that by 2050, electrical propulsion will become the standard.
Yeah, so Ganesh, I mean, I think one of the pieces here, and as I was describing in the beginning of in the introduction of the presentation, you know, the applications that are generating these simulations and linking those together are interesting, but what about the requirements that are defined, how you trace those, how do you verify that the actual performance parameters you need are connected back to the simulations and back to the overall product?
Well, I mean, the answer is simple. It's Teamcenter. They're able to manage everything together in Teamcenter. And in fact, one of the things that they're able to get is a productivity improvement from the first to the second generation of about 50%. And all of that by understanding what happened in the first round and connecting all of that to the second generation. So.
Okay, so again, you know, the point there is the excellent applications to perform the kind of work that we're seeing in simulation, and then connectivity and traceability through Teamcenter to enable that.
Absolutely.
Okay, Ganesh, thank you so much.
Thank you.
All right, the next portion, and you can see we're basically walking left to right, top to bottom. And we're going to highlight a little bit around PCB and manufacturing in the electronic space in the next section. And with that, I would like to welcome Oren Mauner to the stage to highlight a bit about what we have going on with a company called Phoenix Contact. So,
okay, thanks, Jim. Hi guys, my name is Oren Mauner. I am from the Valor division of Mentor Graphics. It's my first PLM Connect, so I'm happy to be here and walk you through Phoenix Contact, which is a nice story around digitalization in PCB manufacturing and PCB assembly. I have to do maybe a disclaimer. I don't have any nice videos about cars or jets or e-copters, so, you know, but I hope you'll find the story interesting. So I'd like to start with maybe a short introduction about who Phoenix is. So Phoenix is a global manufacturer of electrical components and industrial automation. They do a lot of different products, about 6,000 different products, 50,000 PCBs every day. They're, you know, this kind of classic German OEM, which is family-owned, 11,000 employees. We're showing now the headquarters in Bad Pyrmont in northern Germany. And they're what we like to call a vertically integrated OEM. So that means they're doing all of the design in-house, but they also manufacture all the products, they do all of the PCB assembly, and they do all of the box build in-house. So they're a good candidate for full, you know, digitalization from design through manufacturing. And that's really what, you know, the Valor division has been doing there for the last couple of years, implementing the story. So I'd like to talk a little bit about, you know, what the challenges were that Phoenix was facing. And one of them was, you know, the need to continuously change their products, continuously innovate and bring new products to market. They wanted to be better than their competition. They wanted to listen to their customers, and they wanted to be there with new products before their competition. So they wanted a quick turnaround between design through manufacturing, but they of course wanted to retain the high quality of the solution that they're providing. So they didn't want to, you know, do anything and impact the quality. And they wanted to leverage the fact that they have this in-house manufacturing, because a lot of their competitors were using contract manufacturing, which takes a longer time to move than the design through manufacturing process. And as we heard from one of the presentations before, you know, moving data from design to manufacturing is always an issue, also with PCB. And we'll show a little bit, you know, how this was impacting Phoenix and what they chose to do with that. The other thing that they wanted to do was reduce the manufacturing setup time. So they didn't want to spend the whole day getting a new job on the lines, because, you know, if you're only going to make 10 PCBs of this job, you can't afford a whole day to set it up. And finally, as they were going to smaller and smaller lot sizes, even maybe lot size 1, they really wanted to know that their process was validated very quickly, because they just don't have the time to validate the process for a long time.
I think that's an interesting piece, because historically we think of these lot size of 1 as a consumer-oriented activity, but it's not unique to consumer-based activity. It spans in manufacturing, and as we saw from Mouse earlier, even down the individual vehicle. So this lot size of 1 is a recurring theme that we continue to encounter with our customers and with the thinking that we have in our products.
Yeah, I mean, I think it's dripping down slowly to industrial automation as well. And Phoenix's customers have been requesting different products to suit their specific needs, and that's why Phoenix has been broadening the range of products, making more and more product revisions, and making these batches very smaller. Okay, so let's try to see what we've done there and how we've kind of taken this, digital innovation platform and the whole story of the digitalization to the PCB assembly story. So the traditional approach, was always to do a lot of validation on the actual line. So you would create the programs, and then you would take them on the line, and it would take you between a couple of hours to a full day to actually validate production. And one of the things you can see there on the left is what we used to call sticky tape. You would actually take sticky tape, apply it to the PCBs, and run a couple of boards in production to make sure the components are in the right location, that you don't have any rotation issue. And of course, that's a very inefficient process. And with our digitalization project, we were able to actually do a lot of offline validation. So we've been able to create a virtual twin of the PCB and the virtual twin of the process. We can now actually see every component, if it's rotated correctly, if it's in the right location. We can also generate all of the programs before needed, validate that they're okay. So really do a lot of this validation offline, without needing the assembly machines, and really making the ability to move between products to products much, much quicker. And going back to the discussion before about the design through manufacturing and how it's been impacting, so it's also been a big issue for Phoenix Contact. And this is really a place where I think we can, bring down the silos, we can break the barriers, and allow for better flow. And let's hear from Axel, the chief of product engineering in Phoenix, what he has to say about this.
In order to speed up between design and development and production, we have an interface, and our interface is CAD layout department. And in the past, we did this manually. There was no direct connection, no link between these departments. It was human work. But now we try to find a way how to speed up this. And we found a way with a software solution. And with this, we speed up a lot, and we avoid failures.
So we used to say that there's always a wall between design to manufacturing. So also in Phoenix, this wall existed. And the design guys would kind of chuck some files across the wall and hope somebody in manufacturing gets it, and then does a lot of reverse engineering. But now we've actually created a digital flow of information from design to manufacturing. Everything flows through the systems and allows for much better automation and a much, much faster process there. And again, this is Phoenix leveraging the fact that they have in-house manufacturing, that they trust these guys, they can pass all the data, and there's no issues of trust or things like that. So this was the first thing we did there. The other thing that we did there was everything around the shop floor execution and collecting the data. And what you can see on the left there is actually a picture of a chart, a progress chart from one of the largest contract manufacturers in the world. This is in their Shanghai facility, a picture taken about 6 months ago. And you can see that still today, people collect most of the data in PCB assembly manually. They have these kind of charts. And of course, this is very subjective. It's very hard to get access to this type of data. So nobody in the corporate really know exactly what's the efficiency level, how good are we manufacturing, are we on schedule. And what we did there was really deploy our Valo IoT of manufacturing, our edge device, which is able to connect to all of these different products, different machines, collect all of the data in real time, and create a digital twin of the production. As you can see in the dashboard below, we can now show actually what is happening in real time on the machine level, on the line level, on the site level. And as this is online, anybody can access the information from a phone, from a tablet, from a PC, anywhere around the world. So this makes this type of data much, much more accessible to the Phoenix guys.
So Oren, you know, from time to time, I'm asked by any number of people about this notion of dashboarding and KPIs and visibility to the information that's flowing. Is this a configuration process, or is this a customization process? How are we actually implementing this, and how are they implementing it at Phoenix Contact?
So actually, it's a platform, so it's very easy to deploy this, very easy to install. Most of the stuff is plug and play. We can install it and start getting the data. And really, most of the dashboards are pre-configured, preset to allow a lot of quick visibility and an easy deployment. Of course, in the future, today, this is mostly running on-site and on-premise, but in the future, this type of data can be easily made available on the MindSphere platform, allowing them to also access this data in MindSphere and do a lot of things with it on MindSphere. The other thing is that we are standardizing the languages of the machines. So the edge device knows how to talk to the machine in its proprietary protocol, but exports kind of a standardized language, making it much easier now for the Phoenix IT team to engage with the data and connect their own supply chain, quality metrics, any kind of enterprise system which wants real-time data from the machine, and now they can get it, so it makes it much, much more accessible. Now, if we were talking about, the fact that our batch of products is only 10, we have to be very quick to decide that our process is in control. When we were making a batch of 100,000 PCBs, we could spend a couple of minutes until we have 100 PCBs and make sure processes validate, maybe fine-tune it. But if the batch is 10 PCBs, we can't decide to, that the process is out of control after 3 or 4 PCBs, because, that's a lot of money wasted and 40% of the production batch. So we really have to know very quickly what's happening, is the process in control, and this really allows us to do that. So this really allows us, because of this real-time nature, to be able to do this kind of very small batch production and even lot size 1 or very small lots. Now we're collecting all of this data, we're giving the KPIs, we're giving the real-time dashboards, but we're collecting a lot of data. And what are we really doing with all of that data? So the last thing that was implemented there to kind of complete this digital thread is our big data analytics solution. And here the ability is to take terabytes of data and data collected from a lot of machines, a lot of lines, different factories, over different products, over a span of maybe 6 months, even a year, and start looking at that data to see, what's the actual root cause. So we might be seeing some defects, but we don't really know why they're happening. And here we can try to actually understand what's the root cause analysis. We might be finding the defect in a specific inspection machine or a specific functional test, but it might be occurring very earlier in the process. And only by taking all of this massive amounts of data can we actually do this. So now this gives Phoenix the ability to actually go and do some deep analysis and try to understand why their production has issues, fix that, and try to predict also what is happening in the future. And again, Phoenix has this kind of program now for this zero defect quality initiative, and this is really helping him in this, because this allows them to really improve the manufacturing processes, understand why things are happening, and continuously make improvements. So this was another thing, and really I think, as Tony Hemmelgarden spoke yesterday and introduced the PCB assembly manufacturing as part of the Digital Innovation Platform. I think it shows nicely how these three things that we've implemented there provide a real digitalization thread and provide them with the ability to be much more competitive in the market. So this is a great story about Phoenix, and obviously has given Phoenix a lot of advantages and the ability to be more competitive in the market. But I want to ask ourselves, what does this mean to us, and what does this mean if we take another look at this? And really this is going to allow us to automate manufacturing. It's going to allow us to make manufacturing a lot cheaper. And now we don't have the factories to be in very low-cost areas, so we can actually bring factories much closer to where the demand is and where the markets are. So in the future, we can definitely expect the factory to be maybe, just a couple of miles down the road. So we'll be able to go online, configure our products. They'll be built overnight in a batch of maybe 1 or 2 products and shipped the next day right to our doorstep. So for us as consumers, this is going to bring a big change. It's going to have a very positive impact on the environment, reducing shipping costs and reducing time of moving these products, to where the markets are, and really make it probably a better experience for all of the consumers there.
Okay, very good. Oren, thank you.
Thank you, Jim.
Well, one of the pieces that Tony mentioned yesterday was around autonomous vehicles and the operation of those autonomous vehicles. Of course, we saw the scary video of the kid, and I have 4 kids, and seeing a kid run out in front of a bus is a really, emotional thing for you to think about. But the next topic that we want to highlight is around autonomous vehicles. And I have the great pleasure of having a colleague, Jan Lurdan, to highlight some of the activities around this. Now, one of the pieces that we're trying to do as we look at the Digital Innovation Platform, we're highlighting different areas around the platform, the domains, and the collaboration tools. And in this case, we're going to be drilling into some more detail around electronics, software, and simulation. And with that, I'd like to introduce Jan Lurdan to highlight a bit on autonomous vehicles. Jan?
Okay, well, thank you, Jim, for the introduction. And I will indeed speak about our autonomous technologies in context of autonomous driving, which is, of course, one of the disruptors in the automotive industry, along with electrification, along with increasing connectivity of cars, leading to new forms also of mobility. And you see some data points in terms of what these disruptions mean in the automotive industry. Like, of course, a lot of new vehicles coming out, which are electrical vehicles, hybrid vehicles. This, in the middle there, the projection that by 2035, 21 million vehicles will be autonomous driving vehicles, according to one source. And then, of course, these new forms of mobility essentially leading to billions of essentially shared passenger miles, and that coming up also rather quickly. So we're basically focusing on advancing our capabilities within Siemens to support autonomous vehicle development. And I'm going to highlight 2 areas that we really focus on. One area has to do with virtual verification and validation of systems that are used in autonomous driving cars. And Tony mentioned that yesterday. If you really want to go into what the industry calls level 4, level 5, so full autonomous vehicles, well, then you would have to drive quite a lot of miles in order to test the proper functioning of these systems, 8.8 billion miles. And you can do the math. That basically means driving 400 prototypes in parallel, 100 years in a row, and each hour of these years driving these prototypes at 25 miles an hour. So I think you can easily figure out that this is mission impossible with physical testing. You need techniques to do virtual testing, virtual verification, and validation. And we'll talk about that. The second area that we are focusing on is the area of sensor fusion. You know, the sensors are the eyes and the ears of the autonomous driving car. And if you want to go into level 4 and 5, then basically there is going to be an increasing need to do fusion of information of all the sensors that are mounted on the vehicle. The cameras, the LiDARs, and the radars. And so that's another area that we are focusing on. And I will start with a video that essentially is giving you a flavor of some of the capabilities that we have available to deal with sensor fusion, capabilities that came in through the acquisition of Mentor.
We stand poised for a dramatic shift, something unprecedented, bringing new opportunities and new experiences. But getting there means overcoming significant challenges. Advanced driver assist systems traditionally use distributed processing, which increases latency, power consumption, and software complexity. It's time for a new approach. At Mentor, we start at level 5 autonomous, offering a system that can scale down to levels 4 and 3. Introducing DRS 360. Centralized processing of raw sensor data for smarter, faster, and lower-cost autonomous drive systems. Unleash the true potential of autonomous drive with Mentor Automotive.
So what we basically enable with this platform is, first of all, low latency, high bandwidth connection to all the sensors in the car. we can bring the information together in a processing node of that board, which essentially has lots of compute power to do essentially the sensor fusion, but also run all kinds of algorithms, including, of course, deep learning and AI, in order to do things like classification of the objects that are going around or moving around the vehicle. That then basically drives the controls running on that board, and that then connects into, so to speak, the actuators in the vehicle through the CAN bus. Also has the potential, of course, to make applications at lower cost, because having all the power, the processing power in one point, avoids to put processing power at the edge, so to speak, close to where the sensors are. And the next slide gives you a bit of a flavor of, so to speak, what's happening in a board like this. What you see there in the video is actually, of course, images which are recording through a camera sensor. You also see in that image a number of blue dots, which are essentially the information coming out of the scanning LiDAR in the car. And then you see basically how we can fuse the information, and through fusion and processing techniques do classification of objects like the people walking in front of the car, or the cars basically crossing the street. And of course we're playing back here at reduced speed. All of this happens obviously in real time. Let me then go to the second point, which is essentially the capabilities that we have for virtual verification and validation. And essentially, that's where we have our application pre-scan. Pre-scan, which is actually, you can think about it as a very big integration application, because we're bringing together in pre-scan digital twins of the car, digital twins including, of course, the actuators in the car, digital twins of the sensors, digital twins of the world around the car. And really the world around the car needs to be represented in different ways, function of sensors that are used. A camera sees things in a different way, for example, than a radar. And then, of course, all kinds of scenarios, traffic scenarios, and so on. So we're bringing that together in pre-scan, and then within pre-scan we can basically test all these scenarios fully virtually. And what you see on the video there is actually testing a system for emergency braking, similar to that system that you did see yesterday in Tony's presentation. And so you can see that we can simulate the working of that system in different light conditions, during the day, at night, different weather conditions, because these systems have to work when it's raining, when it's fog, and things like that. Thousands of scenarios we can generate, we can execute, and therefore we connect to high-performance computing for this. And secondly, we also make it possible to run those scenarios actually in real time. And why is that important? It is important because when you think about functional digital twins, like Bob Trecapelli talked about that yesterday evening, when you think about functional digital twins, you will frequently get into a situation where you need to create digital twins that combine software with hardware. Like think about running simulators, or think about hardware-in-the-loop setups. Hardware-in-the-loop setups, for example, where in terms of doing these tests, you would be replacing maybe a camera model, replace the simulation model by maybe a physical camera, and then still use, for example, the simulation tool to create the environment that that physical camera would be looking at. Or what you see on the right there is what we call vehicle-in-the-loop testing, where actually we are connecting that simulation environment running in real time to a real vehicle, where the simulation environment takes control on the actuators in the vehicle, on the sensors in the vehicle, and makes the vehicle then think, through simulation, that it is maybe operating in a city environment. And this makes it then possible to do tests for autonomous driving in the real vehicle without being, for example, in the city environment, but rather driving the vehicle on a big open proving ground or a big open parking lot, and where the simulation environment makes the vehicle think it is in a city environment.
Yeah, Jan, I think this brings forward a pretty important point. As you watch the company as we've grown over the last many years, You've seen a number of technologies that we've brought together as companies and now colleagues working together to solve these kinds of challenging problems. I would just submit and maybe ask for your comment about how these different puzzle pieces are fitting together. And you know, you can see the outcome of it. I think we still have work to do, but you're starting to see the strategy behind these different technology pushes that we've been driving most recently with TAS and with Mentor before that, and several years ago with LMS, and simulation in the loop, making sure that we can ask performance questions, get those answers, be able to plug in hardware in the loop, and start to really drive this whole virtual prototyping and physical parameter management that we need in this world. Could you just comment a bit on that as well?
Just maybe a few things, Jim, as also visible on this slide. Actually, to run these kind of scenarios, you, for example, need to connect in 3D multi-body dynamic models. Those are, you know, part of capabilities in SimCenter 3D. You need to maybe couple in what we call their 1D multi-physics models. That's what you use to represent the actuators in the vehicle. All of these things need to run in combination through co-simulation and actually in real time in order to enable some of these hardware-in-the-loop scenarios that you are looking at. And of course, we use them in terms of, you know, management of this information. We couple all of that, of course, into Teamcenter, and quite a lot of extensions have been put into Teamcenter in recent years to really not manage only the, so to speak, the CAE and 3D simulation models, but also manage a lot of the, you know, functional information that basically defines the functional digital mock-up, you know, information from 1D simulation, control models, and things like that. And maybe another point of integration is also what we have been doing meanwhile with connecting that simulation environment into the DRS 360. And you see that on the slide here. What we do with our simulation environment here is that we create virtual images of what the sensor could look at. Like you see on the top there, at the left, a virtual image of a LiDAR sensor, or a virtual image that we would create that basically would be an image coming out of a camera. And we can numerically inject that into the DRS 360, and then essentially on the DRS 360 check fusion algorithms for the sensor data, as well as some of the classification algorithms running there. So what we do here in this combination is quite unique, you know, because we actually create a development platform, if you want to think of it like that, that makes it possible to virtually check the sensor fusion algorithms, you know, image classification algorithms, do all of that without having a need, so to speak, for real data recordings. And then let me finish with this slide. The slide here basically speaks to how Siemens is also a partner of choice for development of autonomous driving proving grounds. Like, for example, we announced early in May the fact that we are the strategic simulation partner for the American Center of Mobility. You know, and that's a big proving ground that is being established in the Detroit area. I believe it's about a $150 million investment going into this. And what you see on the video on the left is essentially how we have been simulating, you know, with pre-scan, the different layouts that are being implemented, you know, on the proving ground. And the video on the right is also an interesting one. It basically points to the fact that we also have, at Siemens, our own autonomous driving vehicles. And we basically use these vehicles on proving grounds already in the Netherlands, essentially to, for example, check the capabilities that we have in our simulation solutions, to check, for example, the capabilities of vehicle-to-infrastructure, vehicle-to-vehicle communication, to be able to do things like platoon driving. And again, think about the example that Tony showed in his presentation yesterday morning, you know, the trucks, and the trucks basically running behind each other. That's platoon driving. We can simulate all of these things in pre-scan, but we also have the capabilities to do, you know, checkpoints in terms of how good it is that we simulate using our own autonomous driving vehicles. So let me finish with this slide. Autonomous driving is a critical enabler for improved road safety. And what I show you there on the left is a, so to speak, a graph from, so to speak, the European Traffic Security Center. Shows essentially the objective that the European Union had put for itself in 2010 to kind of, reduce with 50% the amount of, casualties, road casualties by 2020, so over a period of 10 years. That's basically the dashed line. And what you see in the solid line is how things have been evolving. And what you see is that until 2013, we were pretty much on track. But then from 2013 on, things kind of stabilized at around 25,300 road deaths, road casualties in Europe. And so no reduction anymore, and basically pointing to the fact that the safety measures, of course, obviously reached their limitations, and that in order to have a further reduction, indeed one has to push further on the systems for assisting drivers and of course moving into autonomous driving. Why is that? It's simply because of the fact that a lot of these deadly accidents are accidents where essentially the driver plays a role in the accident. So, driver assisting systems, autonomous driving is a critical part of essentially further making progress on road safety. And with the techniques that we are developing within Siemens, we obviously try to deliver a contribution to reaching these objectives of increased road safety. Thank you.
Jan, thank you very much. Yeah, it made me think that, so we like to have hardware in the loop, and a new acronym would be HOL, which would be humans out of the loop. So we'll continue here with a very interesting talk about Factory of the Future. And I'm going to bring a colleague to the stage that highlights that. This has a lot to do with actually, once again, as we saw with the aircraft, some of Siemens' use of our own tools for enabling this, but also some of the important elements that we're doing to address Industry 4.0 and beyond with closed-loop manufacturing. So, Alistair Orchard, I'd like to welcome you to the stage to highlight Factory of the Future.
Thank you. 1, 2. Thanks, Jim. And thanks, Jan, you blew my mind, as usual. I am going to talk today about actually one of the holy grail goals of digitalization, and that is personalization. We all like personalization. We all like the personal touch. And that could be anything from a thank you note that someone hand wrote us. It could be that good feeling when our favorite song pops up on Spotify. It could be when we walk into our local coffee shop and the barista's already prepared our latte. We like it because it makes us feel special. In fact, about 3/4 of us prefer buying from companies that have this personalization concept built in. But those examples I gave you, they're all services. And it's pretty easy to personalize a service. You can do it at the last minute. You can normally automate it pretty easily. And the cost of personalizing a service isn't that great. When I'm actually making something, when I want to personalize a product, well, that's a whole different ballgame. And in order to illustrate that, I'm going to use an example that I think we all know. That's the sports shoe. We go into the store, we buy a sports shoe, seems pretty easy. But the journey that sneaker's been on is something which really blows my mind, and I'm going to walk you through it. So the journey of the sports shoe really starts with market research. Market research targeting you or your peer group. That market research is then passed over to design teams. And design teams in sportswear really are artists. They're sketching these shoes on pieces of paper. And that's not just a a fake illustration. That's exactly what they do today. They then send those pieces of paper to the production teams to make prototypes. Now, earlier in a presentation, you heard about design teams sitting next to production teams. Well, in sports shoe manufacture, most design teams are sitting in the US or in Germany, whereas the production guys are in China, in South Korea, in Malaysia. So this piece of paper go all the way around the world, and the prototypes come all the way back again. And they're never exactly what was expected. So they're marked up, sent back again, and this iterates 3, 4, 5, 6 times, sending prototypes back and forth around the world until a kind of final prototype is made and a small production run is tooled up, maybe 10 shoes, and they're put on the feet of athletes who provide subjective feedback about how the shoe's performing. It's a long story. Final tweaks are made, the design is frozen, and finally production can start ramping up. And that ramp up is very painful. Lots of waste product gets made. And this is because the entire production run is 100% manual. So in China, Malaysia, and South Korea, there are armies of people manually making shoes. And just the top 2 manufacturers, they make 1 billion pairs of shoes every year. And they're all put on shipping containers and shipped back across the ocean to your local store. And this entire process takes between 18 and 24 months. So how on earth do you personalize that? No one's going to wait 2 years to have a personal pair of shoes. And the answer to this kind of conundrum is actually a concept that we've been talking about for a while now. It's the idea of the smart product. And this really unlocks personalization because smart products, they don't need market research. They can extract requirements directly from individual people. Requirements, goals, targets, constraints. They don't need designers because design rules can be built into the generative engines, generative design engines, that can then use those constraints to design themselves. They also don't need physical prototypes and subjective testing because, as we saw from Jan's presentation, that can all be done in software now. They don't need expensive, wasteful ramp-up in manual factories because that can also be done in software and in simulation. We'll see that a little bit later on. And because we know exactly how to make these now, then we can automate that process. We can shrink those factories down. We can bring them back on shore and make shoes far more quickly and efficiently. And of course, IoT allows smart products to understand their own condition, to maintain themselves, service themselves. And as you can imagine, just think back to that original cycle. The smart product in these 3 phases can radically change that business process, really compress it down. And the goal is not 24 months, but actually just 24 hours for a lot size 1, personalized shoe from order to delivery. And that sounds like an awful lot of time taken out of the process, and it is. We're confident about that, though, because we've already done it, not with shoes, but with our own manufacturing processes in our own factories. So this one you see here, this is Hamburg. We talk a lot about Hamburg because it's kind of cool. Here we're making lot size 1 from order to delivery in 24 hours. So it's exactly the target for sports shoes. Today on the shelves, sports shoes actually have about a 40% variance in key quality metrics. We're making 1 product a second in Hamburg, that's 1 million a month, with about 1,300 variations and configurations, and we're hitting 99.9985% quality. So it's a big transformation in the way that we make our products, and we can apply that directly to all kinds of manufacturing, including shoes. And of course, to do that, you've heard this from us many times now, you can't do that just with 1 or 2 point solutions. You need a platform, a digital innovation platform, and you need to address the entire value chain. But you hear a lot about the extremes of the value chain. We talk to you a lot about about digital twin of product, about the digital twin of performance. I'm going to focus in, for the Factory of the Future discussion, on that middle bit, the often forgotten manufacturing process. And it's called the Factory of the Future because here we are combining the digital twin of production with the real production in a very innovative way, which should resonate with anyone who is from the PLM side of the business. Okay, so how does it work? Well, first of all, we need to understand our factories, and so we actually design our machines in the virtual world, our machines, our robotic systems, and we use a tool for that called mechatronic concept design. That's really a kind of rebadged NX. So it's the same multi-physics environment for designing and simulating our machines that you use for your products today. And the really cool thing is that as we put the machine through its paces, or the robot through its paces, we actually generate all of the automation code necessary to run that machine in the real factory. So we give it a new product, we ask it to work out how to manufacture it, and it generates its own code. Maybe even more cool, through a process called virtual commissioning, that digital twin actually teaches its physical counterpart how to manufacture that part. Okay? So simulation, code generation, validation, and then commissioning without the need to interrupt and disturb the factory with expensive and time-consuming manual commissioning. We do that for machines, but we actually also do it for people. So we use Jill, and Jill, we give her the product we want to manufacture, and we ask her to go through all of the time-consuming effort to understand how to make that safely and effectively. And once she's done that, she actually teaches her counterpart on the shop floor how to manufacture with the same concept of virtual commissioning that the machine made.
So Alistair, in this example, I mean, it's in the right, are we looking at a virtual reality or augmented reality view of that assembly process that's being learned by the worker, or how is that actually interacting?
Yeah, Jim, so this whole concept works for kind of traditional work instructions, electronic work instructions, but actually the closer that we get to a lot size 1, complex, non-repetitive tasks, then augmented reality in this case becomes a real bonus because it's incredibly intuitive and the teaching can be done online and not offline. There's a lot said about augmented reality and the challenges of implementing that. First of all, the hardware, it's still not quite up to scratch, but even the software, standalone augmented reality systems really haven't shown their promise yet. But we're chipping away at that concept within Siemens. So if you take a standard offline, standalone augmented reality system, the first problem is, in order to get it to work, you have to author all the content, and that's horribly time-consuming. I'd say it's even impossible for a lot size 1. In our case, the augmented reality is just opening a window on the digital twin. So it's just giving the real operator a chance to look through Jill's eyes to see the digital twin in action. And that's the digital twin of the product and also production, because it's got all the animations for the assembly in. And that's kind of comes for free because it's integrated into the digital.
Yeah, so as I was saying in the opening, you know, we're driving a lot of virtual reality into our different products, and we want to make it as interactive and available for users to experience virtual reality around their products as possible. And augmented reality is a layer on top where you get the real space engaged with the virtual space and be able to drive things like electronic work instructions and other activities that you need to around the production process.
You can see that in action in our digital enterprise walkthrough down the corridor. One of the other challenges of augmented reality is actually the accuracy of superimposing the product over the physical part. And so our manufacturing engineering team out of Israel has been working really hard on that. And the example that you see out on the digital enterprise booth shows a real innovation in accuracy, allowing us to use augmented reality for very high fidelity assembly processes. Because it's plugged into the digital enterprise platform, there's a final benefit to this approach. Normally, if you use augmented reality, once you've done that, you then got to walk over to the MES system and type what you've done into it. Whereas here, we're following the hands of the user, and we're automatically confirming the operations, we're validating what's been done, we're recording any defects or deviations, we're recording all of the material that's been consumed, and that's all going automatically into the as-built. Must hurry up. Now, all our machines and their people, they understand how to make their parts. But a pair of shoes has got maybe 30 parts. One of our industrial controllers has got maybe 1,000 parts. A jet engine's got 6,000. Manufacturing a product is much more than just making its parts. It's putting it all together in a coordinated flow. And that's even more important when I'm manufacturing a lot size 1. And that's where manufacturing planning comes in, because what comes out of that is this manufacturing blueprint that you see at the bottom. This is a bill of process. One bill of process for every variant that we'll make. That's 150% bill of process. And we derive from that an individual manufacturing blueprint for every single individual product and personalized product that's going to be manufactured. And we just publish that. We test it and validate it in simulation, and we publish it into the MES system on the shop floor. The MES system's job is then to guide the real product through the factory, just like the simulation. Okay, so how does that work? Well, we have our digital twin of our machine. It declares its capabilities. We have the bill of process full of steps with capability requirements. And then our MES engine has got what's called a capability matching algorithm. It's able to match requirements with capabilities. And so on the shop floor, in this case in Hamburg, as the product reaches a certain manufacturing point, it calls out to its digital twin and says, hey, what do I do next? We then run our capability matching algorithm. We identify, in this case, the right person. We push the electronic work instructions to them and get them to do the job, validate it, and then send the product on to the next stage of production, where capability matching may well identify a robot as the next best operator. Download the set points and part programs for that robot, get the job done. And in this way, we can take any product, we can personalize it, customize it, validate it in software, and without any reprogramming of the MES system of the automation, without any business logic on the shop floor, the bill of process coming directly out of PLM will drive its own production and get the product made right first time. You can come and see that in our showcase. So we've got the entire environment running. We're making about 7 variants of our nanobox, and you can watch those being made. And I just want to impress upon you how important this is, not only for increasing efficiency, increasing quality, but revolutionizing business models. Because in the future, we're not going to be buying shoes, we're going to be renting shoes, just like we rent videos. Nightflix is my invention, so, yeah. But this is coming. And so when you're wearing kind of a unique pair of shoes that's been designed just for you, that's been made in the last 24 hours in a local factory in Phoenix, and when manufacturing is driving the US economy again, I want you to remember that and wish that you'd applauded even louder at this point in the presentation. Thank you.
All right, Alistair. Okay, we're approaching the home stretch, and Tony highlighted a great example in Bugatti in his presentation yesterday, and I'm excited to have a highlight. I had a chance to have dinner with Frank, who you'll see in the video in a few minutes during this section of the presentation. This is an engineer of engineers in my mind, really just a brilliant person and able to apply all kinds of engineering approaches to some very tough problems. And so here we're going to be talking a bit about mechanical, of course, simulation manufacturing, in particular additive manufacturing. And with that, I would like to welcome Aaron Frankel and Paul Brown to the stage to highlight this last example.
Thank you, Jim. Good morning, everyone. I'm Aaron Frankel.
And I'm Paul Brown.
If you were to ask an engineering executive what additive manufacturing is for, chances are they would explain to you it's for rapid prototyping. We must change this perception. This is because when you industrialize additive manufacturing to make useful parts at scale, you get tremendous value in your products from your manufacturing process and your business. Mouse McCoy shared with you his vision of the opportunity. Tony shared with you the story of Bugatti, and Paul and I are going to dig into it a little bit deeper. That is the Bugatti Chiron. That car travels well over 400 kilometers an hour. That's faster than the speed a jumbo jet lifts off into the sky. And the challenge for Bugatti is keeping that car safely on the ground at extreme speeds without compromising its performance. Now, when we drive a normal car, at normal speeds, it's the weight of the vehicle that keeps the tires in contact with the road. But when you're Bugatti and you're looking to push the envelope of speed, you need to start to think differently about how you design that vehicle in order to keep the tires in contact with the road without losing control and taking away performance. And what we'd like to do is share with you some more details about how the Bugatti engineering team, along with a team of partner companies, reimagined a system of this vehicle in order to get more performance.
You see, one of the key things, as Aaron mentioned, is keeping the vehicle on the ground. Keeping the vehicle on the ground dependent on the road conditions, whether you're flying down the Autobahn or whether you're on windy roads, you still need that same performance and feel. You need to be able to drive that car with confidence. So the key is reducing turbulence, reducing drag. Obviously, to get a vehicle to run that fast, you want to remove as much weight as possible, as much power to weight ratio to drive forward. And also make everything more aerodynamic. And so that combination of requirements have to be built in and have to be analyzed and processed using the digital twin. And let me explain why you need the digital twin to do this. So if we move on and just look at the current idea of taking this process through, the challenge the engineers at Bugatti found was their wind tunnel testing could maxed out about 186 miles an hour. Now, as you've heard from Aaron already, the top speed of the Bugatti is way over that 180 miles an hour. So you can't physically do it by using traditional methods. You have to change the process. You have to use the digital platform. You have to start pulling things together to understand and predict the analysis. So you saw there both the vehicle on the road, plus the effects of the airflow on this rear fin. The rear fin, rear wing is determined to keep the vehicle on the ground. And using Star CCM Plus to take those extreme speeds and analyze performance in various conditions. So now you can see the actual rear wing in action. This is like a dynamic rear wing. It adjusts in position based on the driving conditions, whether you're on the Autobahn, whether you're on country roads. Depending on speed, you've got control systems that do that. And you can see that we've actually simulated this. Now, the more astute amongst you may notice that the design that you can see there is where we ended up at, and where the Bugatti people drove towards to reduce weight, because what they decided to re-engineer their process was to bring in additive manufacturing and actually can produce not prototype parts, but print in titanium real production parts. And that's the key message. That's one of the things we hope you take away from this, is we have to move additive manufacturing into an industrialized method that allows us to scale from whether it's lot size 1 or lot size 1,000. And that's one of the key things that we're trying to do inside of NX and across the whole Siemens platform into additive manufacture. So if we move forward, so this was the traditional. So we're going to show you a little bit of how this was all pulled together. This was the traditional, the parts, the components that you saw, machined, assembled, and it gave the performance characteristics, but obviously taking weight out to drive that power-to-weight ratio down, increase that power-to-weight ratio, improve performance. And you can see what we've done is taken those parameters in, doing some optimization, using topology optimization, building from that design using convergent modeling to be able to go through and build a design that can be practically used in production, not just a prototype, to be able to add traditional type geometry plus the stylized design to get a highly performant part that's lightweight and meets our performance characteristics and can deliver the game-changing type performance that we want. So this part, you're seeing a mixture of topology optimization, convergent modeling, realized shape. Those technologies are all built inside of the NX platform. And combining that through into additive manufacture, single platform without having to convert data, without having to move out of the single environment, which reduces your performance.
Today, when we try to manufacture these parts, we can't use conventional methods because the geometry is so complex. And so what tends to happen is companies take that design, they design the auxiliary geometry around it to prepare it for printing, which holds it in place, which absorbs heat, and then they generate the output file and they send it to the printer and they wait and see what happens. They look to see if the part was a success or if it had failed. Maybe it had distorted. But when we do it this way, we add risk and cost, and our vision is to industrialize this technology through advanced simulation tools that allow us to predict the performance of the printing process. This way we can see whether or not the part is going to distort during the build process, and then we can automatically compensate for that distortion in the design application, output the proper file and send it to the printer, so when we get to printing, we have more confidence that we're going to be able to get what we intended to. And we're also investing in areas to innovate and realize new capabilities for closed-loop monitoring that will allow us to observe what's happening during the printing process, take that information and help us understand whether or not there's an issue and immediately react to it, so we don't have to throw that entire build away and we end up with the parts that we expect. Now, another major challenge is on the post-process side. This is the finishing of the parts. What we tend to see is that it's a very manual process, that we're actually
we would probably say that's not part of the digital thread, right?
This is absolutely not part of the digital thread.
Actually, can I also add, nor is it innovation, an innovative use of a screwdriver to remove that build area. So.
This is happening in production today. If we want to industrialize this technology and use it at scale, we must automate the process. Thankfully, we have over 50 years of experience in automating, machining of capabilities directly inside of the same system. We have the ability to generate the tool paths to drive the CNC machines. Our system can recognize where that auxiliary geometry is and automatically create the tool paths needed for the machines to machine away that geometry. We can automate this process so that we can get to scale production. We've tied the entire digital thread from requirements all the way through to the finished part.
Yeah, so let's just recap what we're talking about. We're talking about industrializing additive manufacture to scale from lot size 1 to what you need for production, whether it's thousands, tens of thousands. Taking requirements, feeding them through the whole process, building on the digital twin, bringing in information to design, manufacture in a single system without having to translate data, associative, iterative design to the end final system.
So this reimagined wing system we debuted at Hannover Messe back in April, and we have it here in the Solution Center. Please take a look, but I'd like to share with you a short message from the sponsor, Frank Gutzke, of this project.
To do a technical thing like this, which is highly complex, you need to do a lot of steps, and you have to find the right way for that step, because you have to start with an aerodynamic simulation, CFD, and you have to combine this with a multi-physics simulation to find out all the forces which are going in things like that. And what we have done in the past is to use a lot of different softwares to make it, a lot of different products. And the problem is that in every step, if you have to bring the data into the next step, you will lose this data. And with this new software from Siemens, our plan was to start in one software and to go through every step with the same software, with the same digital twin. And that is what we have done. From the start, from the aerodynamic simulation, up to the last step. The last step is the milling of such part. You will bring, after 3D printing, such a part on a milling machine to bring all the holes in it. And even that is done with Siemens software on a numeric, which drives the milling machine. And so we have found a new way with our partners from Siemens to be faster and to be better than before.
We accomplished together as a team significant results. We accelerated the innovation process by as much as 10x. We reduced the aerodynamic drag on the vehicle, and we were able to lightweight the wing system by 50%. I believe the future is going to be better than the present because the tools that we use to design this system are accessible to you. And with creativity, I believe that teams are going to be able to elevate the performance of their products, their manufacturing processes, and their businesses. The tools are available today. If you have questions about them, feel free to come talk to us in the Solution Center. Thank you very much for your attention.
Thank you.
Okay, well that brings us to the end, and I'm just really excited about the technologies that we're able to share with you today, how those are linked together, and how they help companies innovate more efficiently and quickly with our digital innovation platform. We saw the opening example with e-aircraft, the example with Phoenix Contact, quite a bit of interesting information around autonomous vehicles, factory of the future with Alistair, and how we're evolving not only what we do at Siemens, but also working with our customers to increase their ability to deliver products that are exactly the fit for what the customer wants. And then, of course, the truly exciting Bugatti, which is an unbelievable vehicle. So our platform is here today, what you've seen in this presentation are products that are working and being used in production today. And so we're excited about how these are helping break down these barriers, breaking down domain barriers between electronics and mechanical, between software and electronics, across the entire life cycle of your products. So with that, I would like to thank you and wish you a very pleasant conference this week. I would stay in the air conditioning. I think yesterday was 109 outside, although I'm told it's a dry heat, so you shouldn't be sweating as much. Thank you very much for your attention. Hope you enjoy the conference.
Thank you, Jim. Once again, a big round of applause for Jim and his team.